Computer Science 407, Numerical Analysis. Gaussian Elimination with Scaled Partial Pivoting. As you may be able to guess, in this section of the book we'll introduce some improvements to naive Gaussian elimination, since there are some problems with the approach that we developed in the last section. A bit of warning, this is the third longest section in the book. I attempted to cut it down a little bit, but you'll find more details in the text. Some of them I'll skip an example or so. Okay, so last time we saw that naive Gaussian elimination can fail. Consider the following linear system: 0x1 plus x2 equals 1, and x1 plus x2 is equal to 2. Naive Gauss would attempt to subtract some multiple of the first equation from the second equation to produce 0 as the coefficient for x1 in the second equation. This, of course, is impossible, so the algorithm fails, especially if a11 is equal to 0. If a numerical procedure actually fails for some values of the data, then the procedure itself is probably untrustworthy for the values of the data near the failing values, and we're going to see in more than one way. So on the last slide we saw that a naive Gauss can fail. Here we'll see that it can fail in more than one way. Consider the subsystem epsilon x1 plus x2 is equal to 1. x1 plus x2 is equal to 2, where epsilon is a very small number different from 0. When we do the back substitution phase for naive Gauss, we get x2 is equal to 2 minus epsilon to the minus 1, divided by 1 minus 1 over epsilon. And that's approximately 1 there, because again epsilon is quite small. And x1 is equal to epsilon to the minus 1 times 1 minus x2, which is approximately 0. Now, because epsilon inverse, or 1 over epsilon, is so large, this calculation is performed by, when this calculation is performed by a computer that has fixed word lengths, then for small values of epsilon, both 2 minus epsilon to the minus 1 and 1 minus epsilon to the minus 1 would both be computed as minus epsilon to the minus 1. You can see that this is going to give a pretty wrong answer, since 1 plus 0 in the second equation does not equal 2. And 1 does not equal 2, except in Bertrand Russell's developments, but we'll save those for some theoretical math. So basically we can conclude that for values of epsilon sufficiently close to 0, the computer calculates x2 equal 1 and then x1 equal to 0. The correct solution for that system is x1 is equal to 1 and x2 is equal to 1. So the relative error in our computed solution for x1 is extremely large, about 100%. So there's a simple way to solve these problems, and let's take a look at how we can do that. So a simple solution is to actually just reorder each of the equations. So for the first set of equations, we can have x1 plus x2 is equal to 2, and 0x1 plus x2 is equal to 1. Now that's pretty easily solved by the fact that x2 in the second equation is 1, and by back substitution x1 is equal to 1. So by reordering the equations, we were able to solve this much more simply. Now let's take a look at how the second set of equations can be reconfigured to make things easier on us. As for the second set of equations, we have x1 plus x2 is equal to 2, and epsilon x1 plus x2 is equal to 1. After forward elimination, this becomes x1 plus x2 is equal to 2, 1 minus epsilon x2 is equal to 1 minus 2 epsilon. Then, from the back substitution, the solution can be computed as x2 is equal to 1 minus 2 epsilon divided by 1 minus epsilon equals 1, and x1 is equal to 2 minus x2, so 2 minus 1 is equal to 1. Notice that we do not have to rearrange equations in these systems. It's only necessary to select a different pivot row. The difficulty in the second set of equations is not simply due to epsilon being small, but rather it being small relative to the other coefficients in the same row. If you're interested in more details on how the erroneous solution gets derived using naive Gauss, you can look at page 83 of section 2.2 of the text. Now let's take a look at partial pivoting. And this is the strategy we'll use in this chapter. Gaussian elimination with partial pivoting, we'll actually be using scale partial pivoting. But Gaussian elimination with partial pivoting selects the pivot row based on the row with the maximum pivot entry and absolute value from those in the leading column of the reduced submatrix. Two rows are interchanged to move the designated row into the pivot row position. This is contrasted with full or complete pivoting. And Gaussian elimination with full or complete pivoting selects the pivot entry as the maximum pivot entry from all entries in the submatrix. This complicates things a little bit because some of the unknowns are rearranged. And we also need to interchange both two rows and two columns, so we get more interchanges and more work. In practice, partial pivoting is almost as good as full pivoting and involves significantly less work, and anything that involves less work I'm all for at this point. However, there is little, if any, theory to justify partial pivoting. It's primarily heuristic and gut instinct, but in most cases it works well. So, a couple words of warning with partial pivoting. Simply picking the largest number in magnitude, as is done in partial pivoting, may work well. The row scaling does not play a role, and the relative sizes of the entry in the row are not considered. Systems with equations having coefficients of disparate sizes may cause difficulties, and we should probably view those with suspicion. They're going to be more difficult problems. Sometimes the scaling strategy may ameliorate these, sometimes it may not. The book develops a Gaussian elimination algorithm with scaled partial pivoting, and we'll talk about the pseudocode given in this section, which contains an implicit pivoting scheme. So here's another hard example. Let's consider this augmented matrix 2, 2c, 2c, 1, 1, 2. And c is a parameter that can take on very large values. Following our strategy, we would select row 1 as the pivot row since it has the largest element in the column. This is going to lead us to an incorrect solution. Now, since the multiplier is 1/2, one step in the row reduction process brings us to the following system. 2, 2c, 2c, 0. We get the 0 in the first column, second row, which is what we want. 1 minus c, 2 minus c. Now, suppose we're working on a computer with limited word length. So in this computer we would obtain 1 minus c is equal to minus c, and 2 minus c is also equal to minus c. Again, because c is a parameter that can take on very large values. So what we end up with is 2, 2c, 2c, 0, minus c, minus c. So as a result of solving this for y, the second value, we would get 1 and x is equal to 0, when the correct solution was actually 1 and 1. On the other hand, Gaussian elimination with scaled partial pivoting selects the second row as the pivot row. The scaling constant is 2c1, and larger the two ratios for selecting the pivot row from 2 divided by 2c, or 1, is the second one. And that allows us to obtain the correct answer. So, these simple examples should make it clear that the order in which we treat the equation significantly affects the accuracy of the elimination algorithm in the computer. In naive Gaussian elimination algorithm, we use the first equation to eliminate x1 from the equations that follow it. Then we use the second equation to eliminate x2, and so on. The order in which the equations are used as pivot equations is the natural order 1, 2, 3, all the way up to n. Note that the last equation, n, is not used as an operating equation in natural ordering. At no time are multiples of it subtracted from other equations in the naive algorithm. From the previous examples, it's clear that a strategy is needed for selecting new pivots at each stage of the Gaussian elimination. Complete pivoting involves searches over all entries in the submatrices for the largest entry in absolute value, and then interchanging the rows and columns to move it into the pivot position. This will be a bit expensive since it involves a great amount of searching and data movement because you're interchanging both rows and columns. However, searching just the first column in the submatrix at each stage accomplishes most of what is needed, avoiding smaller zero pivots, and this is called partial pivoting, and it's the most common approach. let's take a look at Gaussian elimination with scale partial pivoting. Partial pivoting does not involve an examination of the elements in the rows, since it only looks at the column entries. The strategy from the book simulates the scaling of the row vectors, and then selects as a pivot the element with the relatively largest entry in the column. We use an index array instead of interchanging rows. That allows us to avoid data movement, which is an expensive operation, and this ends up being not as expensive as complete pivoting. It goes beyond partial pivoting to include an examination of all elements in the original matrix. Of course, there are other strategies for selecting pivot elements that can be used, but this is the one employed by the book. In regard to order, the algorithm in this section orders the equations in a way that is suitable for the actual system being solved. For the two examples we looked at, the pivot equations 2, 1 would be 2 followed by 1 instead of the natural order. So we would reverse the order for solving those, particularly in our first example. The order in which the equations are employed is denoted by the row vector, and this is script L1, script L2, all the way out to script Ln, where the script L sub I are integers 1 to n in a possibly different order. We call this the index vector. And the strategy to now be described for determining the index vector is termed scaled partial pivoting. So, for scale partial pivoting, at the beginning of the algorithm, we compute a scale factor for each equation in the system. We call this scale factor S sub I, and it's the maximum of the absolute value A sub ij for 1 to n. We record these numbers in the scale vector S1 to Sn, and then use the equation for which A sub I1 divided by S sub I is the greatest, and we'll let L1 be the first index for which the ratio is greatest. So that'll involve changing the order in our index vector. Then we'll subtract the appropriate multiples of L1 from the other equations to create 0 for each x1 except the pivot equation. So how do we keep track? Well, at the start we'll let L1, L2 to Ln be 1, 2, all the way out to n, so it's a natural order. We then select j to be the first index associated with the largest ratio in the set. The absolute value of ai1 divided by s sub I for I is 1 to n, and then we interchange the first occurrence of that, lj, with L1 in the index vector. Next we use multiples al sub I1 and al sub I1 times the row L1 and subtract from equations L sub I for 2 through n. It's important to note that only entries in L are being interchanged, not the equations themselves. This eliminates a lot of time-consuming and unnecessary process of moving coefficients and equations around in the computer memory. If you've ever done row interchanges in linear algebra, you know that it takes a bit of time even on paper. This will complete the first step in our algorithm. For the second step, we'll scan the ratios A L sub I2 and compare those divided by S of L sub I for 2 through n. If j is the first index of the largest ratio, we interchange L sub j with L2 and L. Then the multipliers A L1 L sub I2 divided by A L2 2 times the equation L2 are subtracted from the other equations, and that gives us the zeros in the second column. So, at each step k, we select j to be the first index corresponding to the largest of the ratios. We interchange L sub j and L sub k in the index vector L, and subtract the multipliers times the pivot equation L sub k from the others to get 0 in the kth column. Notice that the scale vectors are not changed after each pivot step. Intuitively, one might think that after each step in the Gaussian algorithm, the remaining coefficient should be used to recompute the scale factors, instead of using the original scale vector. You can do this, but it's generally believed that the extra computations are not really worthwhile for the majority of linear systems. In our discussion of this algorithm on the last 6 slides, we've used quite a bit of notation, subscripts, and it's probably gotten quite nasty and confusing at various points. So let's take a look at an example to see how to clarify things. In fact, examples usually do. So here we're going to go with an example from the text that's labeled a larger numerical example. Example 1 in the text looks at a fairly pathological example and shows the results for no pivoting, scaled partial pivoting, and partial pivoting. In that example, scaled partial pivoting works very well, but there's no guarantee that scaled partial pivoting is better than partial pivoting. So let's look at an example that is not a pathological example. So we have the matrix that's given here, a 4x4 matrix, times a solution vector x1 through x4 is equal to the b sub I. And we start with our index vector, L is 1, 2, 3, 4. And then what we do is we pick the absolute value of the highest number in each row. So S is 13, 18, 6, and 12. And that's our scale vector. So here again is our row or our matrix. To determine the first pivot row, we look at 4 ratios. And the ratios here are 3/13, 6/18, 6/6, and 12/12. Again, we calculate those from our scale vector and the entry in the first column. We select J as the first occurrence of the largest value of these ratios. So, in this case, J is equal to 3, that's the 6/6, for step K equals 1. So what we're going to do is we're going to interchange rows 1 and 3. So our index vector is now 3, 2, 1, 4. And row 3 is going to be our pivot equation. And there it is, highlighted so you can see that's our pivot equation. Now what we do is row 3 was our pivot equation. So we subtract appropriate multiples of it from the others to create zeros in the first column. So we subtract 1/2 row 3 from row 1, subtract -1 times row 3 from row 2, in other words, add row 3 to row 2, and subtract 2 times row 3 from row 4. This gives us the following results. Now, we're going to repeat that step, and in step K2, we use the index vector L is equal to 3, 2, 1, 4 with this matrix, and we scan the ratios corresponding to rows 2, 1, and 4. We get the ratios as 2/18, 12/13, and 4/12. It's important in this case to recall that our scale vector is 13, 18, 6, and 12, and it does not change throughout the process. Again, we could change it throughout the process, but again, it's not thought that that extra computation gives you any more computational power in terms of the solution. So in this case, J is equal to 3, the 12/13. That's the highest of those 3 ratios for step K equals 2. So we interchange J and K, which means interchanging rows 2 and 3. So now our index vector is 3, 1, 2, 4. And you can see we interchanged these 2 to produce this. And row 1 now becomes the pivot equation. So the pivot equation for step 2 in the elimination is now row 1, and L2 is equal to 1. So next what we're going to do is we're going to subtract the appropriate multiples. In this case, it's -1/6 times the first equation from the second, and 1/3 times the first equation from the fourth. This will give us the following results. Okay, repeat a similar process for the third step. And again, we're going to examine the ratios corresponding to rows 2 and 4 because that's what's left in our index vector. And here we have 13 over 3. That's over 18. Again, we're using the same scale vector from before. And the absolute value minus 2/3 is 2/3 divided by 12, which again is the value from the original scale vector. Now, in this case, j is equal to 3, and we're at step 3, so really the index vector is left unchanged. We're exchanging element 3 with element 3, which is row 2. And row 2 is selected to be our pivot row. Okay, so the pivot equation for step 3 in the elimination is now row 2. And L3 is equal to 2, and we subtract minus 2/13 times the second equation from the fourth equation. And it produces these results. This ends the forward elimination phase of the algorithm. And now we do the back substitution. So the order in which the pivot equations were selected is displayed in the final index vector. That's L is equal to 3, 1, 2, 4. Now, reading the entries in the index vector from last to first, we have the order in which the back substitution is to be performed. So we'd start with equation 4. Solution is obtained by using equation L4 is equal to 4 from that matrix to determine x4, and then we can determine equation L3 is equal to 2 to find x3. So in summary, our solution is going to be x4 is 1, x3 is minus 2, x2 is 1, and x1 is 3. Now let's take a look at how we accomplish this in pseudocode. So the algorithm as programmed carries out forward elimination phase on the coefficient array aij only. The right-hand side vector array b sub I gets treated in the next phase along with the back substitution, just a bit before it actually. This method is adopted because it's more efficient if several systems must be solved with the same coefficient array aij but with differing arrays b sub I. Because we wish to treat b sub I later, it's necessary to store not only the indexing array, but also the various multipliers that we were using. And we can actually store these in the coefficient array aij in the positions where the 0 entries would have been created. These multipliers are useful in constructing the lower upper factorization or LU factorization of the matrix A, as we looked at in section 2.1. We're now ready to write a procedure for forward elimination with scale partial pivoting. And this procedure is entitled Gauss. Our approach is to modify the naive Gauss of section 2.1 by introducing scaling and indexing array. So the procedure Gauss will carry out Gaussian elimination with scale partial pivoting on the coefficient matrix aij. Its calling sequence is n, where n is the size of the n by n matrix, the coefficient array, and the index array. Note that we'll use S sub I in this notation, which is the scalar array, or the scale array. Here's the procedure. You can see it's a little bit long and involved. Now, in the first loop up here, the initial form of the index array is being established, namely L sub I is equal to I. Then the scale array is computed next. The statement for k equals 1 to n minus 1 here initiates the principal outer loop. Here the index k is the subscript of the variable whose coefficients will be made 0 in the coefficient array aij. That is, k is the index of the column in which the new zeros are created. Remember, the zeros in the array aij do not actually appear because those storage locations are used for the multipliers. Again, we're saving a bit of space. This fact can be seen in line of the procedure where x mult is stored in the array aij. Once k has been set, the first task is to select the correct pivot row, which is done by computing a L sub I k divided by s L sub I for I equals k to n. Next set of lines in the pseudocode is calculating the radius ratio, called R max. Here you can see where we're calculating R max. And the index j is where it occurs. Now, Lk and Lj are interchanged in the index array, L sub I. The arithmetic modifications in the array coefficient array Aij due to subtracting multiples of row Lk from rows Lk plus 1 through Ln all occur in the final lines down here. First the multiplier is computed and then stored, then the subtraction occurs in a loop. Now, a word of caution, the values in the array Aij that result as output from the procedure Gauss are not the same as those in the array Aij at input. If the original array must be retained, one should store a duplicate of it in another array. So if you want to keep the original stored in a secondary array or out in a file. Now, let's take a look at how we're going to deal with b sub I in the back substitution phase. In naive Gauss, we modified the b vector during forward elimination phase, but we didn't do this in the previous procedure. That was the forward elimination phase. When scale partial pivoting is done, such as in the procedure Gauss, the multipliers for each step are not below one another in the a sub ij, but they're all jumbled around. So, in order to keep things straight, we introduce the index array L sub I in our code. And this will help keep things straight in formulating what b sub I should be. Now we get to carry out the back substitution. And we can begin by solving the equation for the last one for x sub n, and that's a L n n x n is equal to b times ln. And it's pretty easy to figure out what x sub n should be because we're going to divide by a of the index array nn. In general, the solution for x sub I will be in the format given in the second bullet point. Except for the presence of the index array, this is pretty close to what we did in section 2.1 for the naive Gauss elimination. So now we can combine the procedure for processing the array B and performing the back substitution and put this in a procedure called solve, which is shown on the next slide. Here's our solve procedure. Here, the first loop carries out the forward elimination process on array B sub I, using the arrays Aij and L sub I that resulted from the procedure Gauss. Next part carries out the back substitution process. The variable here, sum, is a temporary variable for accumulating the terms in parentheses. As with most of the pseudocode in the book, those in this chapter contain only the basic ingredients for good mathematical software. So if you were doing this for production purposes or to do some real hardcore scientific computation, you would modify it. For example, we ignore some procedures for optimizing code, and you'll notice there's no error trapping. No warnings for difficulties encountered, such as division by zero. This just continues on its merry way. When you're making general purpose software, or you were doing this for production code, you want to anticipate different possible situations and deal with them in a prescribed way. Well, let's take a look at the efficiency of this regardless, and we can do that via the long operation count. So, solving these large systems of linear equations can be pretty expensive in computer time, and we'll see why when we figure out the number of operations. We're only going to count multiplications and divisions. These are called long operations because they're more time consuming than addition. We're going to do a couple shortcuts and lump multiplication and division together, even though division is slower than multiplication. And as a side note, in modern computers, most of the floating point operations are done in hardware, So long operations may not be as significant as they were in the past, but this is still going to give us a good general operational cost of Gaussian elimination with scaled partial pivoting. So let's begin by looking at the Gauss procedure. Step 1, we need to calculate n ratios using n divisions. And then for rows L2 through Ln, we compute the multiplier and subtract row L sub I from that multiplier times row L1, which means we are doing n multiplications per row with a total of n minus 1 rows for a total of about n squared operations in step 1. Step 2, L1 is not affected, nor are the column multipliers from step 1. And this gives us n minus 1 to the 2 multiplications. That should be a superscript there. We include the computation of ratios in our count for the multiplications per row, which is why you see the n. In total, we'll have n squared plus n minus 1 squared plus all the way down to 4 squared plus 3 squared plus 2 squared, and that gives us about n cubed over 3. So basically the number of long operations in this procedure grows like n cubed over 3, and that's going to be our dominant term. Now, for the solved portion of this, the forward processing of the array b sub I involves n minus 1 steps. The first step contains n minus 1 multiplications, second contains n minus 2 multiplications, and so on. So in total we'll have n times n minus 1 over 2. And for back substitution, the first step has 1, second has 2, and when you sum up the numbers 1 through n, you get n times n plus 1 divided by 2. Thus, solving the solve procedure involves n squared long operations. So this leads us to the theorem on long operations. And this theorem says the forward elimination phase of the Gaussian elimination algorithm with scaled partial pivoting, if applied only to the n by n coefficient array, involves approximately n cubed over 3 long operations. Long operations, again, are multiplications or divisions, and solving for x requires an additional n squared long operations. An intuitive way to think of this result is that Gaussian elimination algorithm involves a triply nested loop, which we saw in the pseudocode. So, an N3 algorithmic structure is driving the elimination process, and the work is heavily influenced by the cube of the number of equations and unknowns. Now let's take a look at something called numerical stability. And the term numerical stability of a numeric algorithm is related to the accuracy of the procedure. An algorithm can of course have different levels of numerical stability. This is because many computations can be achieved in various ways that are algebraically equivalent, but they may produce different results. Obviously, a robust numerical algorithm with high level of numerical stability is the most desirable. So, Gaussian elimination is numerically stable for strictly diagonally dominant matrices or symmetric positive definite matrices. And we're going to see those a little bit later on in the book. For matrices with generally dense structure, Gaussian elimination with partial pivoting is usually numerically stable in practice. But there are some unstable pathological examples in which it may fail, and we'll see some of those in the book. As an aside, at this point the author presents some history of Gaussian elimination, and the first versions of this algorithm actually date back to a Chinese mathematical text that dates somewhere between 150 BC and 179 CE. And there's some interesting history discussion in there. So take a look at some of the Gaussian elimination pivoting strategies. The first of these is classical Gaussian elimination with no pivoting. And what we can do is we can think of this as expanding the lower-upper decomposition of the coefficient matrix A in the linear system. And this is depicted in figure 2.2. As we move further down, we reduce this area that is the unexpanded part, and we expand it into both an upper and a lower decomposition. For partial pivoting, we only swap rows, which does not affect the order of the x sub I. In many cases, this is sufficient. And for increased numerical stability, the largest pivot element is used, which requires searching the partial column below the pivot element. To avoid division by zero, partial pivoting swaps the row having the zero pivot with one of the rows below it. To minimize the effects of round-off errors, the row that puts the largest pivot element on the diagonal is always chosen. And here you can see we're interchanging rows and pivots. Full pivoting involves the exchange of both rows and columns. It's less susceptible to round-off error, but has more work in terms of search and data movement. Scale partial pivoting simulates full pivoting by using partial pivoting and a scale vector that contains some information about the relative sizes in each row. The selection process for choosing the most favorable pivot row is a compromise, with only a small increase in work over partial pivoting, but with some of the advances of full pivoting in the sense that some knowledge of the rows is used. For increased numerical stability, the largest possible pivot element is used in Gaussian elimination with partial pivoting, which requires search in the partial column. In practice, applying Gaussian elimination with partial pivoting and back substitution gives the exact solution to a nearby problem. In other words, exactly the right answer to nearly the right questions. An algorithm that does this is called backward stable. Now, Gaussian elimination with partial pivoting is not backward stable for any arbitrary coefficient matrix A, but it is if A is symmetric and positive definite. Last but not least, when you use math software to solve the linear system, you often get an approximate solution along with something called a condition number. This condition number, kappa of A, indicates how close A is to being numerically singular. That means a non-invertible matrix. If kappa of A is large, A is ill-conditioned, and even the best numerical algorithms produce a solution that cannot be guaranteed to be close to the solution. So, for example, if you're using MATLAB and you want to solve a system, you would solve it using the backslash command. For example, x is equal to a backslash b, and from that you would get an approximate solution along with a condition number. So, next time we're going to look at triangular and banded systems. It'll be a bit quicker. This was the third longest section in the book. So, a bit of a longer lecture, and we're going to cover it over 2 days.